Hello, everybody. We are team number 3 talking about the hybrid oxidizer tank fill-in and dynamics. Our advisor is Dr. Jeffrey Santner. Today, we'll mainly be focusing on the Python and ANSYS simulations, as well as the structural design and analysis of our engine, the control system, and finally, our conclusion. A little bit of intro is that this research for the hybrid engine is a subunit of the Eagle ROCKETRY SEDS club founded here at Cal State LA. This is mostly an aerospace club researching different types of rocket engines, which in our senior design project turned out to be the hybrid engine. This club is also a chapter of SEDS, which stands for the Students of Exploration and Development of Space. Below the figure is the entirety of a hybrid engine. In our case, we'll be focusing on the oxidizer tank filling. Our main objectives are to remotely transfer 15 kilograms of nitrous oxide from a commercially purchased vessel, to also create a testing structure for this nitrous oxide pressure vessel that could also be used as a launching pad, and mainly to predict the time taken for this filling process. Now for computational fluid analysis is going to be Orifiel Ortiz.
Thank you, Amy. I will be presenting the Python model that I developed with the help of our advisor, Dr. Jeffrey Santner. The code is based on an adapted equilibrium model which uses CoolProp to find fluid properties. CoolProp is an open source fluid thermodynamic and transfer property registry. However, for nitrous oxide, it is limited to properties found between the triple and critical points. A solution to the issue will be discussed later on. As seen on the figure, CoolProp's validity range is depicted by the lower left-hand rectangle where the saturation curve is plotted. It is valid for temperatures between 182 Kelvin and 309 Kelvin and pressures between 87 kilopascals and 7.3 megapascals. Also, it doesn't have any thermal conductivity or viscosity values for this particular fluid. To mitigate this, work from Richter and Sage was used to calculate the thermal conductivity within the supercritical region. Their work is valid for temperatures between 277.59 Kelvin and 444.26 Kelvin, and pressures between 101.33 kilopascals and 34.47 megapascals. While work from Takashi et al. Was used to calculate supercritical viscosity for temperatures between 298.15 Kelvin and 398.15 Kelvin, and pressures from 102.5 kilopascals and 5.5 megapascals. To calculate the values for temperatures between 182 and 309 Kelvin, and pressures from 87.3 kilopascals to 7.25 megapascals, work from ESDU was used. The validity ranges for the thermal conductivity and viscosity are displayed on the right-hand figure. As seen, the supercritical viscosity is the limiting value for the model since the upper temperature and pressure values are less than those of the supercritical thermal conductivity. Now, to find fluid properties beyond those available through CoolProp, the Helmholtz functional equations are used. As seen, alpha is the Helmholtz energy, delta is the normalized density, and tau is the normalized temperature. Alpha naught is the ideal gas energy contribution, and alpha r is the energy due to intermolecular forces. From here, the other fluid properties are calculated through partial differentiation of the first law of thermodynamics. The following displays the code's logic. The tank is assumed to be initially filled with air at standard temperature and pressure. Those values are sent to a method which updates the tank properties. If the nitrous oxide is in the liquid, vapor, superheated, or supercritical state, the temperature and density will be used to calculate the other properties, which will then be used to find the mass flux into the tank, and ultimately calculate the heat transfer into the fluid. The heat transfer rate helps to find the change in temperature and density, which ultimately helps to find the change in tank pressure. Now, if the fluid is saturated, the temperature and quality will be used instead of the temperature and density. The loop continues until the tank is filled. At 15 kilograms, the graphs are displayed and the program ends. If the total time exceeds 30 minutes, which was chosen arbitrarily, the program also terminates. If an error is encountered during any step, the program will end as well. As mentioned before, the initial temperature and pressures are assumed to be at STP. The tank length is 50 inches, inner diameter is 6 inches, the source tank is fixed at 1000 psi, and the total mass is filled at 15 kilograms. The resultant tank mass and quality as functions of time are displayed on the two graphs. On the left, the tank mass appears to increase linearly with slight decreases as time progresses. This is expected since the pressure differential between the source and oxidizer tanks decrease with time. This is due to the pressure increasing when mass is added into a constant volume. Also, the nitrous in the tank is initially superheated since it is assumed to expand instantaneously to fill the tank volume. This is noted with a quality value greater than 1. The fluid becomes saturated within the first 10 seconds, with its vapor quality slowly trending towards 0 as more of the fluid is in the liquid state. The total process time is also expected to take 389 seconds or approximately 6.5 minutes. This total process time is within an acceptable range when compared to other modeling methods, one of which will now be presented by Miguel.
So hello everyone, my name is Miguel Romero, and I'm doing the simulations on the pressure vessel, also known as the oxidizer tank. So this past semester, I exclusively focused on the oxidizer tank. You'll see here, nitrous oxide is going to be filling the tank. Nitrous oxide is represented in red, and the initial condition of the tank is air, and that's represented in blue. The results in ANSYS and in my MATLAB calculations are similar to Ori's results. It takes about 5 minutes to fill the tank full of nitrous oxide. And so you'll see here this is the tank filling process. As for the MATLAB code, these two figures were calculated in MATLAB, and the boundary conditions for these figures are start at the source tank, go through the ground system piping into, and it ends at the inlet of the oxidizer tank. So this is a steady state condition. The figure on the left is a plot of the mass flow rate versus the pressure inside the tank. And the picture on the right is the total fill time versus the pressure in the tank. As for the ground fill system, the inlet diameter of the oxidizer tank is going to be 1/4 inch, and the inner diameter of the piping system is going to be 1/4 inch. What we're going to do with the source tank is vary the pressure using a pressure regulator so that we could safely fill the oxidizer tank with slower times if we need to. The figure on the left is a diagram of the ground system. You'll see here the similar conditions apply. Red represents nitrous oxide, and blue represents the initial condition where the ground system and oxidizer tank are initially filled with air. And the video on the right shows nitrous oxide flowing through 2 bends and into the oxidizer tank. The bends are going to be 90-degree elbows. As for the mass requirements, we have to make sure we have enough nitrous oxide to fill both the ground system and the oxidizer tank. The oxidizer tank itself requires 15 kilograms of nitrous oxide, and the rest of the ground system adds up to a total of 28 kilograms. And so the N2O source tanks each have 27 kilograms. So the table below shows the cylinder pressure as well as the dimensions. And so we conclude that there are 2 source tanks needed from the vendor in order to ensure we have enough mass flow through the system. And next, Amy is going to be talking about the valve simulations.
Thank you, Miguel. And hello again, my name is Amy Moore, and I'll be talking about the piping and valve CFD analysis. The figure here shows the schematic of our valve layout, where in total we are using 4 valves, 3 of them being normally closed and 1 of them being normally open. Now the valves in blue are representing the normally closed valves, and the one in gray and black is a normally open valve. The valve system analysis was done mainly through the softwares ANSYS and SimScale, and the CFD simulations were performed on a normally closed valve, since 3 out of the 4 valves used are normally closed. The inner and outer diameter of the valves are going to be a 1/4 inch. Here in the figure on the left is a normally closed valve. When at its passive or regular state, the valve is closed, preventing the flow going through the valve itself. The nitrous oxide is not able to go through it. Once an electrical charge is introduced, the red stopper then lifts, allowing the flow to go through the entire valve. The analysis used on ANSYS was approximately the velocity entering and leaving the system at about 3.77 meters per second, and the flow rate being about 3 kilograms per second. Here we see a simplified version of it in order to understand a little bit more about fluid regions and volumes using ANSYS. Due to the complexity and geometry of the valve, it was a bit hard to perform the right analysis using ANSYS. And it yielded the results that we wanted. However, again, the valve itself is a simplified version. Now, software that was really neat is SimScale, where I was able to plug in the CAD model pretty much from McMaster, and then kind of made a replica of the inside of the valve, and then done CFD using that fluid region of the inside of the valve. Now, the velocity at the stopper region on the figure of the right after performing CFD shows that the velocity there is almost 3 times the normal amount. Therefore, the velocities reach close to 9 to 10 meters per second once the valve was lifted. However, following that, the stopper region back to the regular piping, it shows that the volumetric flow, not the volumetric flow, but the mass flow, as well as the velocity of the nitrous oxide, do come back to being about 3 meters per second, concluding that this valve was can be implemented in our system and is within our safety parameters. Now following with the structural design and analysis is going to be Vicente Estrada.
Thank you, Amy. As she explained, I will now be covering the base structure design and analysis of the test assembly. Revision 2 tackled every possible milestone needed to aid the success of this project. However, when looking into the manufacturing process, our design proved to be over-constrained. An over-constrained assembly meant higher cost and less efficient to assemble. This is where the third and final revision came about. We took an over-constrained design and made changes to achieve an exact constrained assembly without hindering the success of the project. 4 major changes were made to revision 2. We began with reducing the number of legs on the base itself. Instead of 5 legs, we went with a 3-leg design. The cup holder on the back leg was also removed, and instead tabs were added on, which will be displayed in the next slide. On the right, we have our strut bar, which is now replaced with a rail beam. This switch got rid of the need for a welding operation. The beam can be extended to accommodate multiple lengths, and instead of welding, it is held in place by pins, making it easier to assemble and disassemble. After better understanding the weld process needed, it was clear we could cut down the height of the tilt plate and reduce it by half, as shown in the image to the left. Image on the right is a closer look to what I had mentioned in the previous slide. From a manufacturing process, it made way more sense to design and weld tabs instead of a cup-shaped design that needs to be cut at a required angle. Prior to making any changes to our design, certain analysis studies had to be done. As a safety check, we started off with some good old-fashioned hand calculations as shown here. Euler's buckling equation was used to see if the beam we had in mind would suffer any buckling during testing. taking in consideration length, thickness, height, and material, we were able to acquire a beam that worked for our assembly. Here we see a few of the hand calcs that were used to help the design of the tabs, as well as figure out what type of pin we would need. Image on the left shows tear out force calculations, and image on the right shows shearing calculations. Once we finalized our hand calculations, we moved on to an FEE analysis. The tabs were analyzed in both the X and Y direction based on the degree of freedom they would see within the assembly. The results from the analysis were pretty rewarding to see, being that the tabs were designed strictly off the parameters gained from the hand calculations. As noted in the legend, we can see that the tabs will not see any alarming stress levels that may cause any issues. This is the FEE analysis done on the base after implementing the changes. New design proved to be as sturdy as the previous design. The only areas of possible concern noted by the analysis would be where the feet of the base are attached, which we can always swap out if need be. This is a visual of the functionality of the tilt plate. This would allow for the truss system to articulate from a horizontal position to a vertical position to ease transportation and mounting of the tank and engine. I will now pass it on to my colleague Alex, who will go over the upper portion of the lunge structure.
Hi, I'm Alex, and I'm going to be discussing the design improvements to the rocket structure. Since optimization and improvement was the main focus of this semester, I'll start by analyzing the primary area of concern of the structure from last semester, which was the load cell compartment. The design consisted of a sliding type of mechanism to which the motor assembly would be guided up the two rods shown, ultimately compressing the load cell and giving us a force measurement. The concern with the system was that it could create a pure bending stress in the bracket, which could be a cause for failure. To check the validity of this concern, we conducted FEA using SOLIDWORKS to look for signs of yielding. As verification of the FEA, a machine design approach was used as well to calculate the stresses in the bracket with the configuration. Examining the FEA here, we see the component's mechanical specifications on the left-hand side and the component in the middle and the legend on the right. The component has a heat map applied to it, indicating the areas where various values of stress are acting. We can apply the legend on the right of the component to quantify the actual magnitudes of stress that are in different places of the component. We can see the chosen material of 304 stainless steel has a yield stress of about 2.06 times 10 to the 8 pascals, which the green region of the component indicates. This FEA alone justifies our concern that the part will fail under the loads we seek to subject this component to, potentially failing somewhere in the green region to the red region of the component itself. When a pure machine design approach is taken, we can analyze the same component with the same force to give us an idea of what the yielding stress could be. Here, we would be looking for the forces labeled R1 and R2, which indicate reaction forces in the component when a force is applied upwards on the bottom protruding portion of the bracket. These reaction forces would be from the bracket being pushed up against the mounting wall and pulled up against the fastening bolt, respectively. Here we can see the approach taken on the right uses two reaction forces to determine the magnitude of stress in the bracket. However, this method would leave us with an over-constrained component. The method on the right simplifies the bracket to a simpler beam load, which when calculated gives us a magnitude of stress that would again lead to yielding, verifying that the SOLIDWORKS FEA analysis is correct. As a result of highly potential failure, a new bracket was needed. A truss prism approach was taken to support some of the load back into the plate, instead of putting one component into full bending. The idea to manufacture this would be to water cut 4 separate triangular pieces and weld them together into the 3D shaped prism that you see here. When FEA was conducted for this new truss support, we can see the same yield stress as indicated for this bracket at 2.06 times 10 to the 8 pascals. However, no yielding is evident here as indicated by the legend. The highest force this bracket sees is about 1.2 times 10 to the 7 pascals. Shear force hand calculations were also performed, yielding a value of 3.4 times 10 to the 5 newtons per meter, ensuring that our existing hardware could be retained. Overall, we think this design, while much more robust than the previous, serves to create a safer and ultimately better component. The last part of concern needing addressing was the slide mechanism that the previous load cell compartment used. Not only was binding and getting stuck a potential risk, but with the redesign of the bracket, a new way of guiding the motor to compress the load cell was needed. The approach used for this employed a hanger type of bracket that would secure the motor during filling and draining, and double as a guide to ensure the motor only goes in one direction of travel throughout the ignition process. A separate, smaller slide mechanism would be bolted onto the load cell, where it would slot into grooves into the newly designed 3D prism bracket. I'll now pass it on to Anthony for the control systems.
Thank you, Alex. For the control system, the goal was to create a graphic user interface that allows operators to control the purge, fill, and drain sequencing of the oxidizer tank, as well as relay telemetry from the system with regards to temperature and pressure from a safe distance. The system will also monitor temperature and pressure and autonomously make corrections when either value reach undesirable levels. The two types of sensors that were selected were the explosion-proof pressure transducer by swage lock, pictured to the left, and the self-adhesive surface thermistor, pictured to the right. The pressure transducer has a pressure range of 0 to 1000 psi, and the thermistor has a temperature range of -80 to 120 degrees Celsius. All of these values are well within the values we expect to see during all phases of operation. We encountered roadblocks when trying to purchase the pressure transducer due to issues on the manufacturer end, and were unable to obtain the transducer or the technical documentation that would have come alongside it, so this has reduced the functionality of the control system. Some additional hardware that was required was a few 6-volt batteries that are used to power the valves that Amy spoke of, and an 8-channel relay module that the microcontroller uses to actuate the valves. Because of the issues we encountered with the temperature transducer, the process that is being implemented has changed. It now starts with the startup process, followed by purging, the filling sequence, monitoring temperature exclusively, and finally venting. This is the final state of the GUI front panel. Some items of note are the emergency stop and emergency stop confirmation buttons, which must both be in the on position to trigger the emergency stop sequence. And the communication port section on the upper right corner is used to allow for the microcontroller, in our case an Arduino Uno, to be changed from one USB port to another and across computers as well. Finally, to avoid any issues, the program should be terminated by pressing the stop button when the program is no longer needed. This is the current block diagram. We will get to know all the individual blocks a little better in just a second. Before we continue though, all constants used for any calculation are placed on the upper left corner, and all inputs are placed on the left side of the while loop, which is the largest rectangle seen on the block diagram. All outputs are placed on the right side of the screen, but are seemingly not plugged into anything. But that is because all calculation happens within the while loop, and the values are sent to the display from within. There are also special conditions that must be satisfied when actuating valve 4, because this valve would be used for venting into a combustion chamber. This should only be used in the case of an emergency or an actual static test fire. And that can be seen by the valve 04 value change on the upper left portion of the screen. Here we can take a better look at how valves 1, 2, and 4 actuate. They are normally closed valves who are controlled by 3 different buttons. These buttons only hold 2 positions, true or false. The logic gate each button feeds into is a NOT gate. This inverts the value and then sends that value to a corresponding output pin. The NOT gate is put into place to standardize how the system operates. Because of how the relay board works and the valve actuates, if the button is not pressed, we want the valve to be closed, but this causes an issue. Because the valve is normally closed and the button is not pressed, this creates a logical 0 as an output. This would then activate the relay, which energizes the circuit and would in turn open the valve. To combat this, the NOT gate is added so that when the button is in the off position, the system will output a 1 and keep the valve in the closed position. Shifting our focus to valve 3, we can see that there are no NOT gates. This is because, again, we want to make sure that if the button is not pressed, the valve remains closed. The only difference here is that valve 3 is normally open. This is to prevent any extra damage in the case of a catastrophic power failure. Valve 3 was selected to be normally open to depressurize the system in case of the aforementioned power failure. With that being said, we want to output a 0 in order to allow current to flow and in turn actuate the normally open valve, forcing it into the closed position. There are a few more logical processes going on with this valve because this valve also regulates temperature and pressure, but we will come back to that in just a second. Here we take a look at the temperature calculation. There are two analog voltage input pins that read the analog voltage from the thermistors and calculate their value in degrees Celsius. The portion marked in the red rectangular shape is a voltage divider circuit used to find the resistance value of the thermistor, and the remaining portion is the temperature calculation itself. This temperature is then sent to temp 1 and temp 2 respectively, and these values are also sent to the temperature control system. Finally, with temperature regulation, we come back to the normally open valve. The logic here is rather straightforward, as the valve is set to open if either the button is pressed or if temperature reaches a certain threshold, in our case 25 degrees Celsius. That is the purpose of the OR gate, whose truth table and valve position is also shown to the right. By releasing pressure from either the line or the oxidizer tank, we can reduce its temperature, and now I'll be handing it back to Ori for some final words.
Thank you, Anthony. In conclusion, the Python and ANSYS filling time predictions, although different, were within 2 minutes of each other. The losses associated from the valves, although minor, increased the total process time. On the structural side, our redesigns reduced the manufacturing complexity and transportation-related complications. Our structural components are able to withstand the engine forces from a static fire. Finally, our control system enables us to conduct the process remotely with minimal user input. We would like to thank Dr. Santner for advising us with this project, ERSEDS for sponsoring our project, GC Valves for donating the project's valves and coils, EMJ Metals for sponsoring ERSEDS with bulk metal supplies, and last but not least, the College of ECST for allowing us to conduct our research. Thank you, and we look forward to the live portion of the expo. Here are our references.